Hi, I'm Wei Wei Wang.
And hi, I'm Neil Knobloch.
Welcome to Module 2. We are going to focus on the STEM and agriculture disciplinary in this module. So as you can see, welcome and congratulations. Now you're on the step 2. So if you finish the module 1, you're very close, two module away, close to the finish line. So in module 2, which is step 2, we will focus on the role of a STEM and F&R disciplinary. So after this module, you will be able to compare and contrast the similarities and differences among STEM and agriculture disciplinary. And you will be able to apply cross-disciplinary approach of a STEM and agriculture into your lesson and curriculum. So let's get started. So here is a scenario that you might be familiar with. A 9th or 10th grade agriculture and mathematics teacher team up to help students develop a plan for a community fundraiser event where they can sell agricultural products that a student grows in school's greenhouse, which we also use in this scenario in our module 2. So as you can see, there are 4 disciplinary here. We particularly trying to close field that you can see from the students that connected to your learning objectives. So they are agriculture, math, science, and technologies. So in this scenario, that why we're trying to integrate the science and mathematics with the career and technical education subjects, we can see there are 3 advantages in here. So one is enhanced understanding of knowledge and making learning more relevant and be more college and career and work ready. For example, the agriculture teacher has his students grow leafy greens in a greenhouse. They want to determine the best growth condition for leafy greens in the greenhouse. The student used technology, which probably sensors, to measure and monitoring the temperature and light in the greenhouse. And they're using, for example, Google Sheet to automatically collect data to show the change of environmental factors in a greenhouse. The student using the data that they collect to manage the greenhouse to provide the best growing condition for their living green. So as you can see, in this scenario, you can use in science, technology, definitely mathematics, and engineering here. So here are, we think, some of why you should integrate STEM and mathematics with a career technology subject. In this table, we provide an overview how science, math, which has been considered as a traditional core content knowledge, versus career and technical knowledge. As you can see, structure of the knowledge for science and math, they are more considered as a formal knowledge. For the technology or agriculture, they've been considered more as applied knowledge. For the different kinds of knowledge, science and math considered as a conceptual or theoretical knowledge. For technology and agriculture, they will consider as more like a technical and contextual type of knowledge. The use of a knowledge for science and mathematics, there'll be more formal knowledge, which students will have like standard tests on those 2 subject area. For technology and agriculture, they be considered as a more like applied to specific activity or knowledge to specific task. The knowledge of selections is non-selective, as I said, as a core knowledge in most of a PK-12 school classrooms. But for technology and agriculture, it's pretty much a selective type of a course that students can do their selection for their subject area. For the purpose of knowledge, science and mathematics using more like intellectual, you need to understand like intellectual content. For technology and agriculture, it's more like a skill training use, the type of knowledge. As for the instructions, science and mathematics is more like an independence, like a standard alone, so you have a standard. For technology and agriculture, actually in your standards that typically will blend in science and mathematics. So it's very integrative type of knowledge.
So now let's transition and think about different ways that scientists, technology and engineers, mathematicians, and then ag-food natural resource specialists think about knowledge and solve problems in their disciplines. So we call these disciplinary ways of thinking. And although this table does show you the 4 different areas on the left-hand side, content areas, let's just walk through them quickly. For science, the way of thinking is known as the nature of science, or as some people have referred to as the scientific method. The process they use to solve problems would be using scientific inquiry. And in the next few slides, we'll go through each of these and share with you what they look like. For technologists and engineers, they use a design process as their way of thinking, and they use then the engineering design process as the way in which they solve problems. Again, we'll walk through those steps here in a few slides. Mathematicians use the nature of mathematics as their way of thinking. They use reasoning and representation as the process to solve problems in mathematics. Agriculture, food, and natural resource specialists or professionals, they have a way of knowing as applied thinking and also agroecosystem thinking or systems thinking in that context. And they use the process of pragmatic problem solving to demonstrate the way of thinking called applied thinking, and they use systems thinking as the process of demonstrating agroecosystem thinking. So now let's walk through each of these ways of knowing. For science, as we discussed, the nature of science is their way of knowing for scientists, way of thinking, and they do this by asking questions about the world, and then they develop scientific investigations to answer those questions. And you'll see that on the right-hand side, there's a scientific method that demonstrates the steps that scientists would go through to do this. This is guided by empiricism, inference, creativity, theory, tentatively and deductive, inductive, or hypothetical deductive inquiry. All of this simply means that it's guided by doing research to gather evidence and then be able to draw inferences or trying to draw conclusions based upon that evidence. So what methods are used? Typically, inquiry-based learning simulates the scientific process that scientists use to solve problems. And if you are trained to teach science, you will be very familiar with the inquiry-based learning method to model the scientific inquiry process for your students. Scientific inquiry process can be conducted in multiple ways and really get generally guided by asking questions, then collecting and analyzing the evidence, and then discussing what the community understandings of that phenomenon would be. So what does the scientific community think about what the interpretations of this evidence, particularly around whatever phenomena that you're trying to consider and solve. So that's scientific ways of knowing or scientific inquiry. Now let's transition and talk about the way of thinking for technology and engineers. So you have a design process as being the way of thinking that is used, and just a difference. So people ask, what's the difference between a technologist and an engineer? They're very blended. They work side by side in many careers, many industries, but by definition, engineers would typically be considered more theoretical and using design tools to create ideas or to create prototypes. once those are manufactured, then what you have is the technologists who are now going to make sure that they work in the real world, or make sure that if there are any problems, they get solved and then get reported back to the engineers. So it's more of an application oriented role. Technology and engineers are complementary with each other around this engineering design process, and this you'll see that this process is iterative, which means that it continues to loop. It begins by asking questions. What is the problem and what are the constraints? Then the engineers and technologists try to figure out what might the solutions be. And then they choose the one they think is the best idea, the best solution, and that's for Imagine. Then they transition to creating a plan by deciding what do they need. And they design a prototype using those materials, and then they take that and create the design, and they test it out and see if it solved the problem that they were working on. Based upon that feedback, they then go to improve, and they ask what worked, what didn't work, how could this be made better, and that feeds back into the iterative process of continuing to then analyzing, well, what's the problem and the constraints, and they just continue to work through that to improve the product that they're designing. Transitioning now to mathematics, the nature of mathematics is a way of thinking for mathematicians. This is based upon the science of order, logic, reasoning, and representation. And so the process that mathematicians use is called structuring. And so they figure out how to structure a problem in order for it to be solved. And they use a number of different ways to then do this. Teachers will facilitate mathematizing for students using inquiry-oriented pedagogy to then help students explain and justify their thinking. As you think about this, it's not just about memorizing equations, but it's really understanding what are the variables, or what are the symbols and the representations that they mean, and then how do they work together to logically work through solving the problem. You'll see that mathematicians will express their ideas or solve problems through kind of three broad categories. The first one is using analogies of things or natural phenomena abstractly. So a good example is when you look at the growth curve of really any living thing, plants or animals, that maps very nicely into a logarithmic equation. And then you see manipulating the abstractions to illustrate new relationships. So there's ways to conceptualize what's going on, and then how do the variables relate to each other in some form of a slope equation. So that's an example of also trying to demonstrate what mathematician, how they think about things. The third one is communicating the abstraction to communicate meaning about a thing or a natural phenomena. So a lot of times you'll see representations, graphs, or some way that you can actually see what the mathematical relationship is regarding some natural phenomena that does exist. You'll see on this right-hand side, it's just a kind of a demonstration of the different ways that a mathematician would think through, and how teachers then try to model that process for their students. So now let's transition to agriculture, or food and natural resources. So in agriculture, there are two ways of thinking. One is applied, and the other one is agroecosystem thinking. So you'll see that it typically is done through inductive problem solving. And so this agriculture as a discipline is very much informed by pragmatic thought, and it's about solving problems in the real world. And you do that through experiential learning and authentic learning. And so there's an element of learning by doing, and you'll see learning in a context, learning through doing projects, and learning through being able to solve problems and explaining that knowledge. The application of it is very much a part of this inductive problem solving. Let's just talk a little bit about systems thinking. Systems thinking is where you zoom out and you see a number of different components and how those components exist and interact with each other. So agriculture and the food system is situated in a variety of different contexts that are informed by social, economic, political, and even the production, the agricultural food system itself. Agroecosystem makes food system decisions that are productively efficient, also so that you know what way we can be most productive in this context, if we're raising plants or animals, and then in which way can we be most cost effective or economical. There's also an eye to being environmentally sustainable, and how do we do this in a way that we actually coexist, we meaning agriculturalists, how do agriculturalists coexist with the environment so it's not deprived or destroyed. And then there's also a social acceptance of consumers of what products are being produced. A recent example of this would be genetically modified organisms are not commonly accepted by some consumers, and so now some farmers are growing non-genetically modified plants, and that's also available in the marketplace for consumers that prefer that. Systems thinking considers the system as a whole and then how these different elements interact with each other. This diagram on the right-hand side shows a variety of different ways that there are elements within, in this particular one, a tree planting scenario, and then how that's all interrelated with the different elements that exist. You can see that systems thinking considers how different elements of the system then affect each other, and there are both intended and unintended consequences as you then make decisions and how that affects other elements of the system. So this chart really tries to pull together these four different ways of thinking in how problems are solved. So as you can see for science, and if you work down the left-hand column there, asking questions, developing and using models, carrying out investigations, analyzing, interpreting data, using mathematics and computational thinking, constructing explanations, engaging in argument of evidence, and obtaining, evaluating, communicating information is the scientific way of knowing, notice, as we've talked about, is inquiry. Engineering, as we've also laid out, uses an engineering design process. Side by side is with technology. You can see engineers break their process down with a few more steps, but technology also follows a very similar pattern. And then on the right-hand side, you'll see mathematics also uses problem solving. And so we just tried to show how these map with each other side by side. And you can see that problem solving is the overarching theme. There are nuances in how each of these ways of knowing, ways of thinking, think about then solving the problem. So in summary, these different ways of thinking really can contribute and flavor an integrated learning experience for students. So think about this, as we just discussed, these differences do exist, and it's because each of these disciplines are defined by a corpus of knowledge and a big word we call epistemic characteristics. It's the assumptions, kind of the philosophy, if you will, the philosophical assumptions and ways of thinking that then represent how professionals in those specific disciplines would solve problems. Disciplines solve problems in similar but with nuanced differences is what we just showed you in the previous slide. And so there is compatibility in how we then bring the disciplines together and we blend them into one so that you can facilitate interdisciplinary or transdisciplinary learning experiences for students. The good news is that you can see that STEM and Ag, Food, and Natural Resources are driven by solving problems. They're done in slightly different ways or nuanced differences, but together, integrated learning uses a way of thinking. Usually it's driven by one of these that represents a discipline, but then there's complementary ways of then adding to the learning process when you mix content and context from the other disciplines in helping to solve that complex problem.
All right, so let's wrap up. We acknowledge teachers from different fields, disciplinary, receive very unique training. So therefore, we spend like 20 minutes to try to help you see each discipline can play a role in your lesson plans, and also help you see the similarities and differences from the agriculture STEM disciplinary, and how could you integrate each disciplinary in your STEM lesson. So using the paper that you write down your ideas of a STEM integration in Module 1, please answer those questions. So you have reflection question 1. What ways of thinking, science method, engineering design process, mathematics structuring, system thinking, will my students be exposed to during my lessons or units of a STEM challenge? Number 2, in what way can I implement a different disciplinary than my own by thinking about the roles that discipline can play, or the thinkings, like discipline thinking that can play? Is it through a co-teaching or a collaboration teaching or team teaching model? After you answer those questions, you should be able to move on to the next step, which is action steps for your lesson plan. Now, let's take a look. The tables that you also used in your Module 1, which we ask you to have a real-world problems, and also think about what are the 21st century skills that your students will learn through an integrated STEM lesson or unit. And then, can you fill the blank after the Module 2? You complete a very fill the blanks for this table. So if you could, congratulations, you have complete a very basic structures for your STEM integrated STEMs in lessons. So hopefully you enjoyed Module 1, Module 2, and then you have the same structure here. So we would like to acknowledge, particularly for our grad students, Brianna Nielsen, and then she really helped us to construct the slide and do a good job for that. So thank you. If you have any question, please contact us.